Hello friends, I am Shayan. Welcome to the another episode of Fact Sci Guide. Thanks for watching this video. Thanks for joining. I appreciate you. Today I am telling I am reading the book written by Stephen Hawking. The name of the book is Brief Answers to the Big Questions. So let's start. Introduction. What Professor what Professor Keith S. Thorne says about Stephen Hawking. So let's start. I first met Stephen Hawking in July 1965 in London, England at a conference on general relativity and gravitation. Stephen was in the midst of his PhD studies at the University of Cambridge. I had just completed mine at Princeton University. Rumors swirled around the conference halls that Stephen had devised a completion argument that our universe must have been born at some finite time in the past. It cannot be infinitely old. So, along with some I to infinity people, I squeezed into a room designed for 40 to hear Stephen speak. He walked with a cane, and his speech was a bit slurred, but otherwise he showed only modest sign of the motor neuron disease with which he had been diagnosed just 2 years later. His mind was clearly unaffected. His lucid reasoning relied on Einstein's general relativity equations and on astronomers' observations that our universe is expanding, and on a few simple assumptions that seems very likely to be true, and it made use of some new mathematical techniques that Roger Penrose had recently devised. Combining all these in ways that were clever, powerful, and compelling, Stephen deduced his result. Our universe must have begun in some sort of regular state roughly 10 billion years ago. Over the next decade, Stephen and Roger combining forces would go on to prove even more convincingly this singular beginning of time, and also prove ever more convincingly that the core of every black hole is inhabited by a singularity where time ends. I emerged from Stephen's 1965 lecture tremendously impressed, not just by his argument and conclusion, but more importantly, by his insignificant insightfulness and creativity. So I sought him out and spent an hour talking privately with him. That was the beginning of a lifelong friendship, a friendship based on not just on common science interests, but on a remarkable mutual sympathy, and uncanny ability to understand each other as human beings. Soon we were spending more time talking about our lives, our loves, and even death than about science. Though our science was still much of the glue that bound us together. In September 1973, I took Stephen and his wife Jane to Moscow, Russia. Despite the raging Cold War, I had been spending a month or so in Moscow every other year since 1968. Collaboration on research with members of a group led by Yakub Borisovich Zeldovich. Zeldovich was a superb astrophysicist and also a father of the Soviet hydrogen bomb. Because of his nuclear secrets, he was forbidden to travel to Western Europe or America. He craved discussions with Stephen. He couldn't come to Stephen, so we went to him. In Moscow, Stephen wowed Davis and hundreds of other scientists with his insights, and in return, Stephen learned a thing or two from Zaldovis. Most memorable was an afternoon that Stephen and I spent with Zaldovis and his PhD student Alexei Stravinsky in Stephen's room in the Russia Hotel. Zaldovis explained in intuitive ways a remarkable discovery they had made, and Stravinsky explained it in mathematically. To make a black hole to make a black hole spin requires energy. We already knew that a black hole, they explained, can use its spin energy to create particles, and particles will fly away carrying the spin energy with them. This was new and surprising, but not terribly surprisingly. When an object has energy of motion, nature usually finds a way to extract it. We already knew other ways of extracting a black hole spin energy. This was just a new, though unexpected way. Now, the great value of conversations like this is that they can trigger new directions of thoughts. And so it was with Stephen. He mulled over the Zaldovis discovery for several months, looking at it first from one direction and then from another, until one day it triggered by a truly radical insight in Stephen's mind. After a black hole stops spinning, the hole can still emit particles. It can radiate, and it radiates as though the black hole was hot, like sun, though not very hot, just mildly warm. Heavier the black hole, the lowest its temperature. A hole that weighs as much as the sun has temperature of 0.0000006 Kelvin. That means 0.06 millionths of a degree above absolute zero. The formula for calculation this temperature is now engraved on Stephen's headstone in Westminster Abbey in London, where his ashes reside between those of Isaac Newton and Charles Darwin. The Hawking temperature of a black hole and its Hawking radiation as they came to be called were truly radical. Perhaps the most radical theoretical physics discovery in the second half of the 20th century. They opened our eyes to profound connections between general relativity, black holes, thermodynamics, physics of heat, and quantum physics, the creation of particles where before there were none. For example, they led Stephen to prove that a black hole has entropy, which means that somewhere inside or around the black hole there is enormous randomness. He deduced that the amount of entropy, the logarithm of the hole's amount of randomness, is a potential to the hole's surface area. His formula for the entropy is engraved on Stephen's memorial stone at Gonville and Science College in Cambridge, where he worked. For the past 45 years, Stephen and hundreds of other physicists have struggled to understand the precise nature of a black hole randomness. It is a question that keeps on generating new insights about the marriage of quantum theory with general relativity, that is, about the ill understood laws of quantum gravity. In autumn 1974, Stephen brought his PhD students and his family, his wife Jane and their two children, Robert and Lucy, to Pasadena, California for a year so that he and his student could participate in the intellectual life of my university, Caltech, and merge temporarily with my own research group. It was a glorious year at the pinnacle of what came to be called the golden age of black hole research. During that year, Stephen and his student and some of mine struggled to understand black holes more deeply, as did I to some degree. But Stephen's presence and his leadership in our joint group's black hole research gave me freedom to pursue a new direction that I had been contemplating for some years: gravitational waves. There are only two types of waves that can travel across the universe, bringing us information about things far away: electromagnetic waves, which include light, X-rays, gamma rays, microwaves, radio waves, and gravitational waves. Electromagnetic waves consist of oscillating electric and magnetic forces that travel at light speed. When they im- impinge on charged particles, such as the electrons in a radio on TV antenna, they shake the particles back and forth, depositing in the particles the information the waves carry. The information can then be amplified and fed into a loudspeaker or on a TV screen for humans to comprehend. Gravitational waves, according to Einstein, consist of an oscillatory wave warp, an oscillating stretch and squeeze of space. In 1972, Rainer Ray Weiss at the Massachusetts Institute of Technology, MIT, had invented a gravitational detector in which mirrors hanging inside the corner and ends of an L-shaped vacuum pipe are pushed apart along one leg of the L by the stretch of space and pushed together along the other leg by the squeeze of space. Ray proposed using laser beams to measure the oscillating pattern of this stress and squeeze. The laser light could extract a gravitational wave's information, and the signal could then be amplified and fed into a computer for human comprehension. The study of the universe with electromagnetic telescope, electromagnetic astronomy, was initiated by Galileo when he built a small optical telescope, pointed it at Jupiter, and discovered Jupiter's four largest moons. During the 400 years since then, electromagnetic astronomy has completely revolutionized our understanding of the universe. In 1972, my student and I began thinking about what we might learn about the universe using gravitational waves. We began developing a vision for gravitational wave astronomy. Because gravitational waves are a form of space warp, they are produced most strongly by objects that themselves are made wholly or partially from wrapped spacetime, which means especially by black hole. Gravitational waves, we concluded, are the ideal tool for exploring and testing Stephen's insights about black holes. More generally, it seemed to us gravitational waves are so radically different from the electromagnetic waves that they were almost guaranteed to create their own new revolution in our understanding of the universe, perhaps comparable to the enormous electromagnetic revolution that follows Galileo. If these elusive waves could be detected and monitored, but that was a big if. We estimated that the gravitational waves bathing the earth are so weak that mirrors at the end of the ray with this L-shaped devices would be moved moved back and forth relative to each other by no more than 1 by 1000 the diameter of a proton, which means 1 by 10,000,000,000 the size of an atom. Even if the mirror separation was several kilometers, the challenge of measuring such tiny motion was enormous. So during that glorious year, the Stephen and my research groups merged at Caltech. I spent much of my time exploring the prospects for gravitational waves success. Stephen was helpful in this as several years earlier he and his student Gary had designed a gravitational wave detector of their own, which they never built. Shortly after Stephen returning to Cambridge, my exploration reached fruition with an all-night intense discussion between Rai West and me in Rai's hotel room in Washington, D.C. I became convinced that the prospects for success were great enough that I should devote most of my own career and my future students' research to helping Rai and other experiments achieve all our gravitational wave vision, and the rest, as they say, is history. On 14 September 2015, the LEGO gravitational wave detector built by a 1,000-person project that Rai and I and Ronald Draver co-founded, and Black and Barry's organized, assembled and led. They registered their first gravitational waves by comparing the wave patterns with predictions from computer simulations. Our team concluded that the waves were produced when two heavy black holes 1.3 billion light years from Earth collided. This was the beginning of the gravitational wave astronomy. Our team had achieved for gravitational waves what Galileo achieved for electromagnetic waves. I am confident that that over the coming several decades, the next generation of gravitational wave astronomers will use these waves not only to test Stephen's laws of black hole physics, but also to detect and monitor gravitational waves from the singular birth of our universe, and thereby test Stephen's and others' idea about how our universe came to be. During our glorious year of 1974 to 1975, while I was detouring our gravitational wave and Stephen was leading our merge group in black hole research, Stephen himself had an insight even more radical than his discovery of Hawking radiation. He gave a compelling, almost airtight proof that when a black hole forms and then subsequently evaporate away completely by emitting radiation. The information that went into the black hole cannot come out. Information is inevitably lost. This is radical because the laws of quantum physics insist unequivocally that information can never get totally lost. So, if Stephen was right, black holes violate a most fundamental quantum mechanical law. How could this be? The black hole's evaporation is governed by the combined laws of quantum mechanics and general relativity. The ill understood law of quantum gravity, and so Stephen reasoned the fairy marriage of relativity and quantum physics must lead to information destruction. The great majority of theoretical physicists find this conclusion aberrant. They are highly skeptical, and so for 44 years they have struggled with this so-called information loss paradox. It is a struggle well worth the effort and anguish that have gone into it, since this paradox is a powerful key to understanding the quantum gravity laws. Stephen himself in 2003 found a way that information might escape during the hole's evaporation, but that did not quell theory's struggle. Stephen did not prove that the information escapes, so the struggle continues. In my eulogy for Stephen at the interment of his ashes at Westminster Abbey, I memorialized the struggle with these words. Stephen gave us answer. Hawking gave us question. Newton gave us answer. Hawking gave us questions, and Hawking's question themselves keep on generating break thoughts. Decades later, when ultimately we mastered the quantum gravity laws and comprehend fully the birth of our universe, it may largely be by standing on the shoulders of Hawking. Just as our glorious 1974 to 5 year was only the beginning for my gravitational wave quest, so it also was just the beginning for Stephen's quest to understand in detail the laws of quantum gravity and what whose laws say about the true nature of a black hole's information and randomness, and also about the true nature of our universe singular birth and the true nature of the singularities inside black holes, the true nature of the birth and date of time. These are big questions, very big. I have shied away from big questions. I don't have enough skill, wisdom, or self-confidence to tackle them. Stephen, by contrast, was always attracted to big questions, whether they were deeply rooted in his science or not. He did have the necessary skill, wisdom, and self-confidence. This book is complication of his answers to the big questions, answers on which he has still working at the time of his death. Stephen's answer to six of the question are deeply rooted in his science. Is there a God? How did it all begin? Can we predict the future? What is inside a black hole? Is time travel possible? How do we shape the future? Here you will find him discussing the depth, the issues that I have described briefly in this introduction, and also much more. His answers to the four big questions, cannot possible be rooted solidly in his science. Will we survive on Earth? Is there other intelligent life in the universe? Should we colonize space? Will artificial intelligence, that means AI, outsmart us? Nevertheless, his answers deeply deep wisdom and creativity, as we should expect. I hope you find his answers as stimulating and insightful as do I. Enjoy. Keep as Thorn, July 2018. Thanks. Introduction is completed.